All right, it is time to get started. Thank you so much for joining us today. This session is on getting started with PASCO Capstone. Capstone is our data collection analysis software for the upper level secondary classroom and college university level classroom. It has features especially for the use of data analysis in the physics and engineering realms, although other subjects find uses for PASCO Capstone as well. I'll talk a little bit more about PASCO's two data collection options shortly. Thank you so much for joining us. In the next hour, I hope to go over two demonstrations that will help you to get started with PASCO Capstone. The first demonstration, and the one that's going to take most of our time, is a impulse momentum experiment. This is a great way to look at a lot of features in Capstone, from how we can create our own displays of data and how we can do some fairly sophisticated analysis. I will end with another demonstration, this one using a different type of sensor, and our more recent line of sensors, the wireless sensor, and it's going to show a completely different way to collect data. In the collision for impulse momentum, we're going to have very fast data collection. In the example of gas pressure and volume with the wireless pressure sensor, we're going to take a look at how we can take more control over the rate at which data is collected to give us the opportunity to enter data that might come from the real world, not just a sensor like the volume. Your microphone is muted. We're expecting a fairly large group of attendees today. We welcome all of you, and we're grateful to have you today. However, if we open up the mics, it gets a little cacophonous. We do wish for your feedback, though, and the best way to give us your feedback is to use the chat window in this GoToTraining interface that we're using for this session. Now, I have a screenshot here of the interface on Windows. It can look different on other platforms, but what I'd like you to find somewhere in this platform, in this window, is a panel called the chat panel. You may need to twirl it open depending on the platform you're on. In that chat panel, you'll have the opportunity to send messages to anyone. We expect that generally you'll be sending these messages to everybody, just a comment, question, or to the organizers only if you wish to just send a question to me and my colleague who are helping you out today in this presentation. So just to make sure you found that chat window, go ahead and send a chat to everybody and let us know where you're calling in from today. The drop down below will let you choose all, the entire audience, if you wish to share that with everyone. All right, Denise, thanks for joining us from Raleigh. Vasek, welcome from Wesleyan, Connecticut. John, Australia, fantastic to have you here. Susan, Georgia, welcome. All right, fantastic. So it looks like you found that chat window. Feel free to use that throughout the session to send a general comment or question to everybody, or just to direct it to us, the organizers, and we will address that. All right. Sometimes during the session, if you're on a single monitor, you may find that this GoToTraining panel gets in the way. If that's the case, you may find something like this orange arrow that you would see on Windows that allows you to collapse this panel and give you more room to view the screen that I'll be broadcasting. Great. Frank, welcome from Missouri, North Dakota, another Australian. Hi, Helen. All right. So we are recording this session, and we're going to give you this recording tomorrow. This session is going to happen fairly quickly. I'm going to go over a lot of features of the Capstone software in this next hour. Probably too fast for anyone to follow along if they're new to Capstone, but if you wish to follow along, it's a great way, if you have the equipment, to get comfortable using Capstone's fundamental features. I encourage you to do so with the recording. The recording will be a link to a posting on YouTube, a unlisted posting, but you can use all the features of YouTube to pause, play, speed it up, and even look how well Google can transcribe my audio. All right. So great to have you here today. My name is Glenn. I work in PASCO's Education Solutions Department. I focus primarily on doing trainings, whether in person, live like this, or creating training videos. And I'm delighted today to be joined by my colleague in the group, Matthew. Matthew, would you like to introduce yourself?
Hi, I'm Matthew. I am also in the Ed Solutions group. I am a curriculum author and trainer as well.
Great, thanks, Matthew. Good to have you. So Matthew is going to be keeping an eye on that chat window to either answer your questions directly via text or to feed some questions to me if they're of general interest. So I'd like to get a little bit to know about a little bit more about your background, especially regarding the use of PASCO Capstone. So in a moment, your screen's going to turn blue, and I'm going to ask a poll question here. This poll question asks you, which best describes your experience, your use of PASCO Capstone? Are you an active user, an occasional user, or are you just taking a look for now? So you'll be able to choose one of those three radio buttons And thanks so much. I see most of you voted already. I'll leave it open for about half a minute more to give everyone the chance to let us know. This will help me direct the depth that we go through today, as well as just to let us know who's looking at Capstone and online training for it. Fantastic. So thanks so much for your votes. I'm going to close the poll now, and let me share with you a little bit of information about your colleagues who are joining in. So we can see that just about a third of you are active users. Fantastic. Just over half occasional users, and about 12%, 1 in 10, taking a look for now. We'll welcome all of you, and even if you're an experienced user, I think you're going to find something new and useful today in Capstone. If you are an occasional user just getting started, much of the content today is going to help you to get started and be more efficient in your use of Capstone. And if you're just taking a look for now, fantastic. It's great that you've joined us. And toward the end of the session, I'll be sharing with you some resources. It includes a link to a fully featured 60-day trial of PASCO Capstone if you want to just take a look. And I'll even leave you with an exercise that you can use to play around and practice some of the things that we do today during the live session. All right, so thanks for your responses to that poll. All right. So our agenda, as I mentioned, are to look at 2 different demonstrations. The first is going to be the bulk of our time together today. It's an impulse and momentum experiment, and I'm going to go the whole way from how do we set up the sensors with which we're going to collect data, to how do we configure displays to appropriately look at the data we're collecting, how do we decide how quickly to record it. We'll also be looking at the core data analysis tools. This has a lot of analysis into it, and we'll be looking at how we can gather our results in various ways, including within the PASCO Capstone software itself. And I'll make sure you're comfortable with the options for saving and exporting the data if you wish to get it out of Capstone or preserve it for later use. The second and shorter demonstration will be an investigation of gas pressure and volume. In that case, we're going to learn a whole new way to collect data. We'll use a different type of sensor, a wireless sensor. And we'll take a look at how we can derive models from the data that we collect, in this case trying to see if we can derive Boyle's law from a quick set of data that we collect on the desktop here, and take a look at how we can transform that to build our mathematical model. I'll wrap it up with a few resources, a homework challenge, and open it up formally to questions and answers, but I welcome your questions throughout via the chat window. If it's a timely question, or even if you're not sure, feel free to send it to us and we will address it. So I mentioned that Capstone is PASCO software for upper-level secondary college university level data collection and analysis with PASCO sensors and interfaces. It is not our only piece of software. We have a piece of software called SparkView, and SparkView is designed for ease of use and use on any platform, from the smartphone in your pocket to the Chromebooks that are so popular in many countries' education systems these days, to Mac and Windows computers. It's designed for ease of use, and it's powerful enough to be used in many classes from kindergarten level up through introductory college and university level courses. We're going to focus today on Capstone. You can even see from the screenshot here, Capstone looks a little more sophisticated, while SparkView focuses on showing you the data and allowing you to open up tools for further analysis. Capstone presents those tools front and center, and we're going to take a look at the key tools today. If you want to learn more about the differences between SparkView and Capstone, I've kind of lighted over many of them. Just Google SparkView or Capstone, and it's going to bring you to a page at our PASCO.com website that does a great job of distinguishing between these 2 pieces of software. So we are going to connect PASCO sensors. So I have a question for you. If you already have some PASCO equipment, what sort of interfaces are you using? In a moment, I'll open another poll, but to make sure you're familiar with the names of some of these things, I'm going to show you some pictures. We have one line of interfaces called the universal interfaces. They include the 550 and 850 interfaces. These are our newest interfaces, and universal is in the name because they work with our sensors back to the late 90s, the Science Workshop line of black sensors and the line of Passport sensors. So these are our universal interfaces. Starting in the late 90s, we had some black box interfaces, kind of the classical initial experience with data logging in education. One of those was the 750 that came in both SCSI and later USB versions. In the late 90s, we had a 500 interface that had a serial connection. And even before that, we had a couple of interfaces, the 300 and the 700 interfaces that connected via serial and SCSI respectively. Around 2001, we introduced blue sensors and blue interfaces. These blue interfaces include things like the Explorer GLX, the SparkLink Air, the first interface, the USB Link, and the most recent that allows you to use your Passport sensors wirelessly, the AirLink. Or you may have some sensors that don't even need interfaces. This is our latest line of sensors, the wireless sensors, and I want to include them there even though they don't use an interface. So if you happen to have some of these PASCO interfaces, let us know in the poll that I'll open in just a moment. And you can see the options there between universal interfaces, the black box science workshop, the blue passport for our blue passport sensors, and wireless sensors, which don't actually require any interface. Or if you're just taking a look at Capstone for now, you may not have any PASCO sensors yet. So you can choose more than one if your school has more than one. And we have most of the votes in here already. Fantastic. Let me leave it open for about 15 more seconds to give you a chance to check all of those that you have in your school system. Great. All right. Let me close that poll. Thanks for your responses. Let me share those with you. We can see that it's a good distribution, and many of you must have more than one of these. Just over half have some of the more recent 550, 850 universal interfaces that use both our black and blue sensors. Just under a quarter also have Science Workshop, the black box classic interfaces. 60% of you have the Passport interfaces that have been around for just over 17 years now, and 60% also are experimenting or are using our white wireless sensors that don't actually require an interface. Fantastic, thanks so much. So the good news is, there are two pieces of good news. One is we're going to cover all of these types of sensors used in Capstone today. And basically, almost all of these interfaces, including those built back in the late 90s, some of them built in the late 90s, work with PASCO Capstone. We understand that these interfaces last a long time in the education system especially, so we take a lot of engineering time to make sure that they are backwards compatible. So which of these interfaces now shown on the screen are compatible with Capstone? Well, of course, the universal interfaces, our latest line, are compatible with PASCO Capstone, both the 850 and the 550. The 750 interface and the 500 interface are both compatible. If it's a USB 750, it's directly compatible. If it is either the SCSI 750 or the 500 that uses serial, we have a USB to serial adapter that lets you use it with Capstone via USB. The only interfaces I'm going to show you that aren't compatible are the age 1997 700 and 300 interfaces that use SCSI and serial. All of the Passport back to 2001 are compatible, and of course our latest line of sensors, the wireless sensors, are compatible. So for the vast majority of you in all of those categories, your interfaces and sensors are compatible with Capstone. All right, so let me jump now into the impulse momentum demonstration, where we're going to learn a lot about getting started with Capstone. And to be honest, the first 15 minutes of this demonstration is about 75% of everything you're ever going to use in Capstone. The remaining 30 or so minutes we have left together is more about just the fine details of it and some specific uses of it. All right. So let me jump over to Capstone, give you the first look during our session today. And this is what Capstone looks like when you open it. Capstone is a computer-based application. It runs on both Windows and Macintosh operating systems. You can tell it's designed for mouse use because some of these icons are fairly small, but we want to surface all of those things that are likely to be used during data collection and analysis. The first feature you may notice in Capstone is big white space here. This is where we're going to primarily interact with Capstone, the data visualization and analysis. And we're going to learn how to make some displays on that space shortly. Surrounding this workbook space, as we call it, we have a typical file menu up top and corresponding icons for doing things like opening and saving Capstone files. We have along the left side of our workbook a bar that we call the tools palette. We'll talk a little bit more about that later, but this is where we can set up our sensors and figure out what data we've collected. This is where the data lives. On the right side, we have a displays palette, and this is where we can choose from the types of displays we'd like to use to visualize our data. Today, we're going to focus primarily on using the graph and the table displays, probably the most commonly used displays in Capstone. Along the bottom is where we have the controls palette. This is where we control data collection, from deciding whether to record or stop collecting data from our sensors, and doing things like controlling how often measurements will be recorded from those sensors, the sample rate. So I'm going to switch over here and show you a live view of my desktop, my physical desktop, so you can see physically what we're going to do to collect some data. And in a moment, you should see on the screen a live view of the number of interfaces sitting here on my physical desktop. And the sensor we're going to begin with to do momentum and impulse is a Passport force sensor. This is the Passport high resolution force sensor. And it has a unique connector like this that all our Passport sensors have. So I need to have an interface to connect this sensor to my computer and use it with Capstone. And as I mentioned in the previous slide, we have many interfaces that support this, from the era circa 2001 Passport USB link to the more recent incarnation of it, the AirLink, that either can be used directly via USB or via Bluetooth to make a Passport sensor wireless. What I'm going to do, though, is use the Passport ports on the 550 interface, because I'm going to show you data collection with both a blue Passport sensor in this experiment and a black Boulder Science Workshop sensor, so we can see how to use both of those sensors. So if I'm using a Passport sensor, it's quite easy. I just make sure that my interface is turned on. This 550 is connected to my computer via USB in this case. I will plug in my Passport sensor. And Passport is so easy to use that I don't actually have to go into hardware setup. I will show you that later, but I can jump directly to getting some data into a display of my choice. I don't even need to know how to use the displays palette yet, because I can choose one of these quick start page templates that show up on any brand new workbook file. So I'm going to choose the first one here, and it's going to automatically create for me on this workbook page two displays, a table display that you can see along the left side of the workbook page and a graph display along the right. Now you'll notice some prominent select measurement buttons. All I need to do to define what I want to see in the table and graph is click on select measurement, and it's going to drop down a list of possible values and measurements that I could put in here. Because the blue Passport sensors are auto-identifying and auto-detected, it already knows that I have this force sensor available. Now for the first column of my table, I'm going to choose time. And for the second, I'm going to choose select measurement, and I'll choose my force. So in a moment when we collect data, I'll have a table of time and force. Similarly, on the graph, I'm going to start with the y-axis select measurement button, click on it, and choose that same force. And I don't even need to go down here to the x-axis select measurement button, because since every graph needs y and x-axis values, it defaults to time. Now I could come and change this to something other than time, but it has defaulted to time, which is what I'm interested in this investigation. All right, Matthew, any questions yet in the chat window that we should address? All right, if you have any questions about what we're covering, don't hesitate to send them to us in chat there. All right, so we have physically connected the sensor. We have displays for it. All I need to do to get some sample data here is press the start record button that is down in our controls palette. And when I hit record, you will see both the table columns populate with measurements coming from the force sensor and those measurements being plotted live on the graph. And you notice that as these values exceed the edges of the graph automatically scales to make sure that by default they are in view. When I think I've collected enough data for my investigation, the record button is now a stop button down in the controls palette, and I can hit stop to stop that set of data collection. Now, every set of data you collect between hitting start and stop, or rather record and stop, goes into what Capstone calls a run. We can see these little labels in the second column of the table and in the graph legend, as we call it. And this run is run number 1. So by default, runs, which is what you get when you press record and stop in Capstone, are enumerated run number 1, number 2, etc. Well, if we want to collect a second run of data, we can just hit record again. And our first one hasn't gone away. We'll figure out in a moment where it went, but we get a second run of data, and you'll see it's enumerated as run number 2. So let me hit stop there. So I'm going to focus on doing a little bit with our second run of data rather in the graph display here. Now, the first thing you may notice is that I could probably improve my display of this data. So I'm going to manipulate the graph and show you some ways that we can change the view. I see Vasek asked a great question. Are there keyboard shortcuts for run and stop? Unfortunately, there aren't. I know that is a popular request, and I know one of our software programmers here is working on potentially adding those in the summer release. But at this time, you do need to be on the button itself with your mouse cursor to run and stop. There are a few keyboard shortcuts in Capstone, but my hope is that summer 2019 will have a set that includes some of the core features like starting and stopping data collection. If you need to do something like automated at this point, there are third-party programs that can press sections of the screen, and I've worked with some teachers who have used that to collect data for 1 hour at noon every day by essentially having a virtual mouse clicking that area. But for now, Vasek, there aren't keyboard shortcuts for that. Thank you for the question. All right, so let's look at some ways we can change our view of the data in the graph. I can directly manipulate this graph as I would a piece of physical graph paper on the tabletop. What I do is just take my cursor and I click and drag in the middle of the graph. And you'll see that as I hold my mouse cursor down and move my mouse around, I get the graph moving around. Go ahead and turn off the webcam for now, so this maximizes your screen view of Capstone. So I'm moving the graph around, translating it. I can also zoom in and out of this graph as if it's made of rubber, better than the real world. what I can do is hover my cursor over the numbers on either the X or Y axis. And when I click and drag any of the numbers on the X or the Y axis, you'll notice that the graph stretches as if it's made of rubber. You'll notice that it's stretching from the origin, 0, 0. So I can do a combination of translating in the middle of the graph and stretching to get a better view of my data. Now, one of the goals of manipulating your view of the graph often is to just make sure that you're optimizing your use of screen space and expand the data so that it fills the screen. There are a number of tools in each of the displays in Capstone, and we're going to focus on some of the key tools in the graph today. The graph toolbar by default is open here when I'm over the graph, above the graph. And if I hover over any of the buttons, I'll get a little tooltip that tells me what the button does. Now, as I'm hovering over the leftmost button in this toolbar, you'll notice that tooltip says scale axes to show all data. And this is what we call the scale to fit button. If I click on it, you'll notice that the axes automatically adjust so that the view of the data is optimized. That is, the data occupies more of the graph display. So probably the most used button here is on the far left of the graph toolbar, scale axes to show all data. Now, you may be wondering, how do I know what the name of the button is? Because it only shows me a tooltip about what it's going to do. The button on the far right of the toolbar looks like a little eyeball. And in Capstone, the eyeball allows you to choose whether a tool is visible or not. And in the graph toolbar, it has a side benefit if you click on the eyeball of showing you the names, the official names of all of these buttons. So if you ever see a PASCO tutorial that says find scale to fit, and you don't know which button is scale to fit, you can use this little eyeball to figure out the name of the tool itself. All right, so the scale fit button is an example of many of the buttons in the graph toolbar. It has two parts. I pressed on the left portion of the scale to fit button, and that caused the action to be initiated here, in this case, changing the graph axes. But many of the buttons in the toolbars in Capstone have a second part, a smaller right portion that looks like a drop-down arrow, and these are basically the options for that feature. So in the case of the scale to fit button, there's only one feature here. It's called auto scale from 0. You may notice that my graph's auto scaling by default just zooms in on both the X and Y axes to make sure that I'm seeing all of the data, but it excludes the origin 0, 0. If you wish to include the origin 0, 0, you can turn on this option in the little black drop-down button called auto scale from 0. At this point, if I go back and press scale to fit, you'll notice that it includes the origin. So notice how many of these graph toolbar buttons have a little option drop-down on the right side that allows you to change the behavior or select an option for that tool. Let me turn off auto scale from 0, at which point scale to fit zooms into my data completely, ignoring the origin itself. All right, so we've looked at scale to fit and the important distinction here between the left and right portions of the buttons that have a drop-down option dialog. Let me show you another button here. The statistics tool looks like a Greek letter sigma. It is also an example of a tool that has two parts. The left part is, in this case, a toggle. It turns on and off a statistical analysis of the active run in the graph display. In this case, you'll notice that as I turn it on and off, I get a visual representation and numerical value for the mean of the entire set of data that I've collected here in run number 2. Now, you'll also notice that this button has a black drop-down menu on the right side. These options, if I click on it, allow me to add or remove particular analyses. So I'm going to add minimum, maximum to mean. And now I can use the left portion to turn on and off these values, but because the right option has selected these 3 values, all 3 of those are going to be turned on. If I want to turn off statistics, I can just click on the left portion of it, and this happens to be a toggle button. Let me show you one more button before we continue on to our experiment here, and that is, you'll recall I collected 2 runs of data, but the first one disappeared in the graph as soon as I press start to collect the second one. This is because there is a default behavior in Capstone's graph to show only 1 run at a time. This is great when you want to really focus the attention or analysis on the most recent run, but we can choose which run we're displaying at any one time and actually turn on both runs if we're interested. The way we do this is to look at the right drop-down portion of this little rainbow triangle. This is called the data selector button. And in this drop-down, you'll notice a list of all of the runs that I've collected that could be displayed in this force versus time graph. Right now, run number 2 is checked. That is the most recent run. But if I want to switch back to run number 1, I check on it. And you'll notice that the default behavior is to switch back to it and turn off run number 2. That's the default behavior of 1 run at a time. So how do I look at both runs at a time if I want to do a visual comparison? Well, that's the function of the left portion of this data selector button. If I click on it, it now allows me to simultaneously view multiple runs. As long as that left portion is clicked down, that is selected, any new run I collect, like this run number 3 I'm about to collect, is shown along with any previous runs. So those are some of the most used features of the graph, and we've seen that we can collect multiple runs and choose to display either the first run, or rather the most recent single run, or all the runs at a time. So do let us know if you have any questions about the basics. If you think about it, we now know how to use a passport sensor, and this is most of what you're going to do. How do I record data? What displays do I select? And how do I ensure that the data is in those displays? How do I view and analyze it? Matthew, are we all good with questions? All right. All right. So, Denise, yeah, good question, Denise. How do I see all the runs in the table? So, like the graph, you can switch between the runs in the table. I'm going to switch by clicking on run number 3 here, and I can see one at a time. If I want to see all of them at a time, I actually need to create additional columns for those additional runs. We're going to look at this again later, but since you asked, the graph, the table toolbar's leftmost button allows me to insert empty columns to the right of any selected column. So let me add 2 more columns here. I now have a shared time column. It's shared by default, but I can go into the options and change that. I have multiple columns now for each run. So I'm going to turn on and select force, run number 2 for the second force column. I'm going to switch and select measurement force for the last column there. And here I can view all across all the runs. So it's a little different in the table. I need to create the column and then populate the column with the run I'd like. Great question, Denise. Thanks for that. All right. Great. All right. Thanks for your questions. Now, I'm going to show you now my favorite feature of Capstone. Capstone's about doing science experiments, but we want to make sure you're comfortable experimenting with the software itself. So Capstone has an unlimited undo. There are 3 ways to access this. In the top toolbar here, you'll see a backwards blue arrow, and it actually tells you this is going to undo and then tells you what it's going to undo. In this case, it's going to undo changing the column measurement. Now, I can also access the undo by going to the edit menu, where I'll see the same thing, undo change column measurement. And I'll see a shortcut to it, Control Z on Windows, as I'm using here, or Command Z on Windows, on Mac rather. So let me just hit Control Z here, and you'll notice that it depopulates that column in the table. Let me hit it again and again and again. I'm just going to hold Control Z here, and notice that it has gone and zoomed back in time through every single thing that I've done in this experiment. Well, as long as I don't make a change right now, I can also zoom forward with this forward arrow, redo, or edit, redo, or Control Y. So I'm going to hit Control Y, and we are now replaying every single thing I've done in this experiment. So I'm showing this to you not because it's typical to redo everything, but because I want you to feel comfortable exploring Capstone's features, knowing that you can always undo them. That applies to everything in Capstone, from data collection to analysis to populating table numbers, etc. Park asked the question, can the table's numbers be represented exponentially? Yeah, it turns out they will be represented exponentially if the numbers exceed a certain threshold, that is, they're very small or very large. We can go into the data summary here and actually describe how we want those numbers to be presented using a gear icon here for the particular measurement. You're going to find gear icons throughout Capstone, and they kind of hide the properties that let you dig down deep into the measurement. So if I were to click on this gear in the data summary panel, notice I've opened the data summary here by clicking on it, and I click on force and get a gear. I can come in here to the numerical format for force, and I can say, you know what, instead of a number file fixed decimals, I'd like to always use scientific notation, or I'd like to define the number of significant digits. And for each of these, if I switch to scientific notation, I can decide a number of significant digits to show and the thresholds where it switches over and so forth. So you can choose how to change the display of the data, as I've shown here, changing it to exponential, using the properties of the data itself in the data summary. While we're here, the data summary is where the data lives, and you can see that for each of the runs I've collected, they are listed here in the summary. So without respect to whether they're displayed in the displays on the right, when you hit record, you get a run collected in the data summary. Thanks for the question, Park. All right, so I would like to actually jump into momentum impulse right now. We now have one of the measurements that we're going to use, the force measurement, that's going to inform us something about the impulse in a collision of a cart and a force sensor. Let me start a new experiment. I'm going to do that instead of by closing Capstone. I'm simply going to go to the File menu and choose New Experiment. Yeah, Vinay, great question. We are actually going to cover that in just a moment, so timely question. I'll show you that in a moment. So I'm going to go to File, New Experiment. Capstone says, hey, You may not know this, but I can only have one file open at a time because we're accessing hardware. There might be some confusion with multiple files. So it asked me, would you like to save the current file? I'm going to say no. We're going to show you how to save files in a little bit. So I'm going to discard this experiment that I've been doing so far and jump back to a new experiment file. So let me turn back on the camera. And I want to show you the actual physical setup we'll be using today. So pan around here. We're going to continue to use the 550 interface. And we're going to use two sensors, and in fact, two generations of sensors to investigate impulse and momentum. So I have at the end of the table here one of our aluminum tracks, a 1.2 meter track. It has on it a PASCO, and I have the same type of force sensor we were just using on the tabletop mounted on the little bracket here at the end. And I have a spring connected to that force sensor. So what we're going to do shortly to measure the impulse, that is the force over time, we're going to collide that cart with a force sensor. We can put various attachments on the end of the force sensor. In this case, it's a very soft spring. And we can measure the force over time if we set it up properly, including what Vinay asked, choosing an appropriate sample rate. Now, we have another generation of sensor at the end, just to show you we can collect two. It is a black Science Workshop motion sensor. The motion sensor works kind of like a bat or dolphin's echolocation. It is sending out chirps when we're recording data from its gold foil. Those chirps are going to bounce off of the back of the cart, and we're going to get information about the cart's position from which it can derive the velocity and acceleration of the cart. So the two things we're actually going to measure here, or we care about measuring for impulse and momentum, are the force, which will inform us about the impulse, and the velocity, which can give us information about the momentum of the cart. So we've already seen how we can connect the passport sensor, but let me show you in a little more detail how we can make sure everything's working for us in Capstone. I'm going to go in this new file to the Tools palette and click on the Hardware Setup button. Because my 550 interface is turned on, Capstone recognizes it, and it shows me a pictorial representation here of the interface. Now, the great thing about Passport is that all I need to do is physically connect to the sensor, and the interface and software will simply recognize it. So I'm going to once again plug in my high resolution force sensor. You'll notice if you look at the Capstone screen that there's no sensor connected currently. As soon as I plug it into an appropriate Passport port though, it's auto-identified and Capstone automatically populates it in the appropriate port. So that's the way Passport works. Simply plug it in, it's identified. Now, we have motion sensors in the Passport line, so we could be doing it with that. We now have wireless motion sensors, so we could be doing that. But I want to show you how we can use Science Workshop sensors, since they're very popular still among schools that have been using interfacing for quite a few years. There are two types of Science Workshop sensor ports. One is called digital. It looks like a old-style quarter-inch stereophone headphone plug, and the other is analog. The case of the motion sensor is fairly unique. There are only a couple of Science Workshop sensors that have these two digital plugs, like the rotary motion sensor and this one. In the case of these sensors, you'll notice one is yellow, one is black. This is simply sending out the signal and receiving the signal. And if we're to use these sensors that have two different color plugs, we plug in the yellow one on the left. So I'll use the digital port here on my 550 for the yellow plug, and I'll use the right digital channel number 2 for the black plug. So my connections are now made for Passport force sensor and Science Workshop motion sensor. Now, if you're looking at the Capstone screen, you may notice that nothing has happened for Science Workshop. That's because the traditional Science Workshop sensors don't automatically identify themselves. All right, that technology came with the Passport line. So let me show you how we remedy that in the software. Basically, when we're using Science Workshop, we need to physically connect our sensors with the physical interface, and then we need to virtually connect them in the image of the interface. All I need to do is click on a yellow circle, the same yellow of the port that I connected the sensor to physically. So I'm going to click on digital channel 1, and it's going to open a list of possible Science Workshop sensors that could have been connected there. Now I could scroll down this list, or I could simply remember that this is the motion sensor and start typing MOT, and it filters down that list of possible sensors to those that start with those letters or include those letters. So here's my motion sensor 2. I will plug it in virtually now, and now I have the two sensors I need for our impulse momentum experiment. All right, now there's something subtle about this experiment that you wouldn't know until you've actually done it. I have done it, so let me tell you about it. The motion sensor and the force sensor are currently facing in different directions. They each have a positive default direction, and right now the motion sensor's positive direction is to the right, and if I'm thinking about the forces exerted on the cart, they are positive to the left from the force sensor's perspective. just because I want to be tidy about this, and this is a physics experiment, I want to make sure that I have a sign correspondence between these two. It's quite easy in Capstone. Before I do my data collection, I'm going to go into the settings for one of these sensors and basically flip the sign. You'll notice that each of these sensors in the hardware setup has a gear, that is a properties button for it. I'm going to click on properties for the motion sensor 2. You'll see a number of properties I can change about it, from zeroing measurements to changing the name of the sensor. What I'm going to choose though is the change sign option. So I know that this is going to make to the left positive now, which corresponds to the positive direction for the force applied to the cart. So I've now changed the sign just to correspond or correlate those two measurements and have the same direction. Right. Kind of a subtlety, you wouldn't learn it until you played around with it, but that's the level of depth that Capstone gives you behind the scenes when you look at the properties for a sensor measurement. All right, I also want to show you once again in the data summary what measurements are available from these two sensors. So I'm going to click on data summary, and you'll notice that hardware setup closes by default. By default, only one of these panels is open at a time. I can change that behavior if I want to, but it's kind of handy just to keep things clean. So I'm going to click on data summary to open the data summary panel. And here I can see that the high resolution force sensor will be reporting force values, and the motion sensor 2 by default can report things like position, velocity, or acceleration. We're going to be using velocity, but this just tells me that it will. And as we saw earlier, this will populate with runs. Thank you, Matthew. Yeah, you do have control over the relative size of the live video and the Capstone screen, so feel free to find a handle between those two sections as Matthew has described in the chat and choose which view you'd like to focus on at any one point in time. Thanks, Matthew. All right, so I am set up in my hardware. My data is what I want to collect. Let's talk a little bit about these options here in the controls palette at the bottom, especially the one that Vinay asked about, the sample rate. Each sensor, when you connect it to Capstone, has a default sample rate. It's appropriate for many experiments, but in the case of colliding that cart with the spring on the force sensor, this actual collision happens very quickly, fraction of a second in many cases. I want to collect a lot of data during that time because in order to determine the impulse, I have to have detailed measurements of the force, basically almost continuous detailed measurements about the force to determine the impulse during that interaction. So I want to change the sample rate of the force sensor from its default that we can see down here in the controls palette, which is 20 Hertz, to a much higher value. Now, if I wanted the sample rate for all sensors to be the same, I can click on this little drop down showing the measurement, or the sensor rather, and I can choose the option here called common rate, at which point I could change the sample rate for all connected sensors in common to the extent that these sensors allow the same sample rate. In this case, though, I don't really have to sample so quickly with the motion sensor, and in fact, the motion sensor, because the way it makes measurements, has a slower maximum possible sample rate. So let me revert back here and choose high resolution force sensor. I would like to change its sample rate to be much faster. So from the default of 20, I'm going to click on the up arrow here to the right of the sample rate representation here, and you notice it jumps in discrete jumps that the sample rate that the sensor supports. And I'm going to jump up to 500 Hertz. It's not the maximum the sensor supports. That's 2,000 kilohertz or 2 kilohertz. But I'm going to go down to about 500 because I know it works for the type of interaction I have here. I'm going to go back to the dropdown for the sensor type here in the sample rate dialog and choose motion sensor 2. For this, I'm only going to bump it up a little bit, 50 Hertz, because I only care about what's the velocity coming into the collision and going out. So, Vinay, hopefully that addresses your question about choosing a sample rate. By the way, I can choose and change sample rates between runs in the same experiment file, so don't worry about, you could collect some data, see if it works, and if it doesn't, change sample rates and record subsequent runs with the new sample rates. I happen to know from previous experiments that these sample rates work well for this investigation. So the last thing I need to do before collecting data is decide, well, how do I want to display this data? For this, I'm going to introduce you to the displays palette along the right side. These are the displays that we can put primarily data into, but other things like movies for video analysis. I'm interested in the graph display primarily for this investigation. So I'm going to hover over the graph display button, and it gives me a tooltip. This tooltip says drag to page or double click to create a graph display. Let me do the first thing, drag to page. If I drag this to the page, you'll notice that there are some blue boxes. And as I hover over the blue boxes, it gives me a preview of where this graph display will be dropped if I release the mouse button. So I could have it on the bottom half right here, or I could have it fill the screen if I drop it in the center. Let me escape out of that though and show you what the other option is. And that is to simply double click to create a graph display. So let me double click graph, and basically it creates a graph that fills the screen. Let me do that again. I can actually have multiple displays in the graph or on the page. So I'll double click graph a second time, and you notice that by default, Capstone puts these two graphs side by side. Now I could be adding other displays, and each time I double click, Capstone is going to resize the previous displays to give me space for the next displays. Let me undo that table though and show you that if I'm interested in two measurements, force and velocity, this isn't maybe the best way to look at it. This would work, having two graph displays, but a disadvantage is I could have force in one of these and its x-axis is independent from the x-axis of the other display, which for example might be showing velocity. So let me undo this and go back to having a single graph. In this experiment, I want to look at two measurements from the sensors, force and velocity. So one option would be to have two y-axes. By default, each graph display has only one y-axis, but if I come to the graph display toolbar at the top, one of these buttons, it looks like an up arrow with a green sparkle, tells me that if I select that, it will add a new y-axis to the active plot area. Let me click on that. Well, I now have two y-axes. I can make one force and one velocity, and that will work perfectly well. Let me admit, though, that I often have trouble distinguishing between which is which. So I'm going to undo that and show you the way that I most prefer for investigations like this, where I'm looking at two different types of measurements and want them to be synchronized in the graph in time. This is the next option in the graph display toolbar. It looks like X and Y axes with a little green sparkly. This is going to add what's called a new plot area to my graph. If I click on it, I now have a new plot area. And what's great about these two so-called plot areas is that they can have different measurements on the y-axis, but their x-axes are synced together. So let me quickly populate these two. I'm going to make the top a velocity for the y-axis, the bottom force for my y-axis, and I'm now ready to collect data. I have my displays, I have my sample rate set. So let me collect a little bit of data here to show you what we can do in terms of analysis. What I'm going to do is hit the record button in a moment and then gently push the cart so that it collides with the force sensor in its spring. And let's see what sort of data we get. So I'll hit record. I'm going to be making sure my hand does not get between the cart and the motion sensor because I want it to be reflecting sound off of the cart and not my hand. So I'll hit record, push the cart, and catch it as it bounces off. All right. So the velocity looks good. It was coming in negative due to my change of sign of the motion sensor. One thing I notice here about the force sensor, though, is I forgot to do something critical. Notice that before the cart collided, there's a non-zero value. It's between 1.5 and 2 newtons. So what I forgot to do is zero the sensor. No problem, though. We have undo, or if you're only interested in deleting the last run, there's a dedicated button for that in the bottom bar here, the control bar. So let me delete the last run. In the case of the Passport force sensor, to zero the sensor, there's a zero button on the sensor. I've just pushed it, and I'll record this again. The nice thing about physics experiments is they're often pretty quick and easily redone. So let me hit record. Stop. And this looks better. I have a zero force before the collision. All right, so let's zoom into the interesting part here during the collision. Now, there are a couple things we want to figure out to investigate the relationship or potential relationship between impulse and momentum. One is the change in momentum, and we can find that from our velocity versus time graph. We're also interested in the impulse, which is the integral of force over time. We can find that by looking at the area under the force versus time curve. And by looking at values in the top graph and areas in the bottom, we'll take a look at some of the key analysis tools in Capstone's graph. What I'd like to do is figure out, well, what was the change in velocity compared to going in before the collision and exiting the collision? We can see it starts out negative going in, positive going out. What was that change in velocity? Well, I could read it off the graph y-axis, or I could get more precise, of course, by using a graph analysis tool. So I'm going to hover over this tool that looks like crosshairs. It is called the coordinates tool. And if I click on the coordinates tool and choose the first option here, add coordinates delta tool, it's going to drop a crosshairs on the top plot area. You'll notice that as I move the crosshairs around by clicking on the center of the crosshairs, the X and Y indicators tell me the position of the crosshairs. And if I get anywhere close to a data point, it jumps onto that data point. By the way, once you've jumped onto a data point, you'll see the color changes to that of the run, telling you you're actually on a data point. And I can now be using the arrow keys on my keyboard to scroll point by point. So I could figure out that the incoming velocity was minus 0.59 meters per second, the outgoing velocity about 0.55 meters per second, and I could figure out that delta. Well, I'm a little too lazy to do the math, so let me show you a quick way to do this. If I right-click, and right-clicking is one of the second secrets of Capstone. There are the gears for properties, and there's right-clicking. If I right-click on my coordinates tool, there's an option here called Show Delta Tool. If I turn that on, I get a second handle, and I can drag the second handle out, and now I get a calculation and display of the change in X, that is the change in time in this case, 0.14 seconds between this first point and the second point, and a change in velocity, which is what I'm interested in. So this is a quick way to determine the difference in X and Y between any two coordinates in your data set. So I've determined the change in velocity. That's going to inform our change in momentum in just a moment. Now, how do I record this? Well, I could have a traditional paper lab notebook and I could write it in there. I could be working in a spreadsheet and type that value in there. Let me show you two things that I could do in Capstone itself if you wish to. One thing I can do is just take a picture of the screen as it currently is showing my analysis. The way I do this is with what's called the journal button. There's a camera icon in the top bar. If I take a journal snapshot by pressing that button, I'll briefly get a thumbnail of the page. And what happens is if I open up this little journal looking book, I see a list on the right side of all the journal snapshots I've made, and I can open these up larger to look at the values. I can save them afterwards to insert them into documents. I could print them directly to a printer if I have it connected. So one thing you can do is take a journal snapshot of any display at any time that you're interested in preserving your analysis. What I'd actually like to do, though, is a little more sophisticated. I'd like to have a table of my results in my Capstone file. So even though I've already built a graph display, at any time I can add additional displays. So let me show you that I can drag table down here, and I'm going to drop it on this little blue box in the bottom half of the page, and it's going to rescale the graph so that it fills the top half and the table fills the bottom half. I don't need so much room for the table. I do need more space for the graph. So this is a good trick in Capstone. If I hover my cursor between the two displays, I will see a dashed blue line. The great thing about this is I can now click and drag and notice that the relative size of each of these displays changes. So I don't have to worry about overlapping them. I can change their sizes simultaneously. So let me give myself a little less room for the results table and a little more room for the table up top. Now, in this case, I'm using this table kind of for results. So let me say, well, this was the soft spring trial. So I'm just going to type soft spring in the first cell of the first column, and it automatically creates a data set for me. Its default name is user data. Let me click on that and choose rename, and I can say, you know what, this is the trial. And I'm going to hit tab, and there are no units, so I'll delete that. And this is where I'm going to describe the trial. Well, second column here, let me type in the change in velocity that I found earlier. So this was 1.14. I'll hit enter and it creates a new user entered data set. This I will rename by clicking on it and say this is the change in velocity. Now I could be as explicit as I want. I can type out change in velocity, or if I want to be more concise, I could say maybe something like delta V. But since this is a science program, let me get rid of that delta and show you that right-clicking is, of course, the way to get to some secrets in Capstone. I'm going to right-click and reveal that I can insert special characters from integral signs to degree symbols to delta. So there's delta V. I'll hit tab, and this is in meters per second. All right, so we've determined change velocity. That will inform our change in momentum. Let me add a column. We saw earlier we can add a column. This column is going to be our impulse. So let me find the impulse in this bottom graph. Impulse is the area under the force versus time curve. And we have a dedicated tool for the area under the curve. Let me show you something critical I did, though. I did it so subtly because it's kind of second nature. If I were to turn on the area tool, by default, it's going to apply the top plot area. Why is that? Well, the top plot area has a very faint blue box around it. It is the active plot area. If I want to apply tools to the lower plot area, I first click on it to move that subtle blue box to the lower plot area, and now I'll turn on the area tool, and it determines the area under the curve. Now, this is the area under the curve for everything, including this little oscillation of the spring here. So I might want to be a little more precise and determine the area under the curve for just this time during the collision. I can do that by adding a highlighter, and I'll add the highlighter by using this highlighter button. I can drag the highlighter over, and you notice that wherever the highlighter is over data, that data is highlighted in yellow, and the analysis tool, in this case area, adjusts itself to make sure I'm only analyzing that section. So let me adjust the box, so I'm determining the area under just the collision curve here, and I can see I'm getting a result of 0.296 there. So 0.296, I'll enter that into the table and call this the impulse. I'll just say J, kilogram meters per second. All right, so I have the impulse, I have the change of velocity. How do I convert that to a change in momentum? Well, let me add a column here for the mass of the cart. So I'm going to click on the first column and add column. I know the mass of this cart is 0.250 kilograms. And then there's mass in kilograms. And now I need to multiply mass by change of velocity to get change in momentum. I don't have to do the math myself, though, because kind of like Excel, I can do calculated columns. So instead of just inserting a column, I'm going to insert a calculated column to the right of change in velocity. As soon as I do that, it gives it a name, calc1, and it has a line up here, much like Excel, that would allow me to multiply the velocity times the mass. To get the mass, I'll right-click, choose Insert Data, and find this mass value of user entered data. I'll hit Enter, and it calculates that for me. I rename this here. This is delta P, change in momentum. I'll right-click to get the delta symbol. Change in P, and that's kilogram meters per second. All right, so you can see they're quite similar. If I want more decimal places here, I can click on the cell and add it there. So pretty close to each other. Now, if we had more time, I'd continue to do further analyses, the hard spring, some clay, change mass, and so forth. And you can see that I could do these analyses in the graph to determine change in velocity and impulse, add them to the table below. And I could do further things like I could determine the percent difference between these two. Now, if you wanted to take your analysis or results elsewhere outside of Capstone, there are some options. First, let me show you I could save my Capstone file. If I go to File, Save Experiment As, I will save this to my desktop. Capstone files are .cap. It's a unique proprietary format, but it opens in any version of Capstone. Works on Windows, Macintosh. You can do cross-computer transfers there. Let me call this impulse momentum with data. Save it to my desktop. Data 2. All right. And now I can close Capstone and open this up, and it will look just like this with all my information, including journal snapshots. Now, if I want to get an image of my graph elsewhere, I can click on the graph and make sure it has a solid blue border along the side and hit Edit Copy or Control-C, Command-C on Mac. And now I could go to applications like Word, and I can say, you know what, I want an image of that graph, so I'll hit Control-V, and I now have an image of that, for example, in a report. Another thing you might want to do is to take the data out of a table. I'm going to click in the table, select Control-A for all values, and I'm going to jump over to Excel. And this is a neat way to get your data into other, oops, sorry. Go back there, Control-A, Control-C, forgot that. And I'll paste it in here. This is a great way to share data between groups. You can collect all the data in the classroom, for example, on a single Google Sheet or Excel document and share it there. All right, so sorry for rushing that, but hopefully that gave you key features for doing analysis in Capstone and kind of a bonus in figuring out how we can use this table for results. All right, any questions, Matthew, about that? Fantastic. So we have only a few minutes left for gas pressure and volume. The good news is it takes only a few minutes. So I've saved this file. I will share this with you afterwards. Let me do File, New Experiment. I will turn off my 550 interface because I want to show you, crucially, because many of you have wireless sensors, how to use a wireless sensor in Capstone. So File, New Experiment. I have all I need to do Boyle's Law, gas pressure and volume, in the form of a wireless pressure sensor, which comes with a syringe. How do I set up a wireless sensor? Well, under Hardware Setup, I'm going to click on it, and all the time Capstone is looking in the background to see if there are any wireless sensors around. This wireless sensor is not currently on, but the neat thing about wireless sensors is I don't need an interface. I can simply turn on the sensor. There's a power button on this one. It uses a rechargeable battery, and it is now broadcasting to any PASCO software in the vicinity that it is available for making measurements. As soon as I turn it on, you may notice in the Hardware Setup window in Capstone, it detected that sensor. The sensor has a unique ID, so you may have 10 of these in your lab. Each one has a unique ID. You'll see a corresponding ID here. And the good news is that the strongest signals, radio signals, show up in the top of the list. So almost all the time, the one at the top of the list will be yours unless your lab benches are really close together. So I've clicked on the pressure sensor. It is now added it to Capstone, and I can now get measurements with that. Now, notice that for wireless sensors, there are sometimes quick start experiments. In this case, there is one for Boyle's Law. Let me show you, though, that I can set up this experiment quickly. I'm going to choose that same template, the quick start template of a table and a graph. I'm going to start typing in some volumes I'd like to use, 50, 60, 55, 50. These will be in milliliters, as I'll specify in a moment. Go down to 15, and I'll rename this volume. Where do I get the volume? Well, I don't have a sensor for it in this case, but I can read the volume off of this syringe that I have. What do I want in the second column of the table? Well, that is a sensor measurement, pressure coming from the sensor. So I'll click on Select Measurement, choose Pressure. For the table, I'll choose pressure for the Y and volume for the X. I don't want time there. I'm not interested in time. But here's my dilemma. If I hit record right now, all those pressures begin filling in. Why is that? Well, the default sample rate for the wireless pressure sensor is 20 Hertz. Let me undo that and show you that what I really want to do before I collect data is to change the sample mode here. By default, in a new file, the sample mode is continuous. That is, sensors data is collected at sample rate. I'm going to choose it, select it as keep mode though. In keep mode, I can hit this now new preview button, and it tells me, well, the current pressure is this, but I'm not recording it. It will only record it if I choose to keep sample. This gives me all the time in the world to connect the syringe to my sensor, select the appropriate volume. In this case, my first volume is 60 milliliters. And when I'm ready, I can hit keep sample. So I'm going to quickly go down the line here of 60, 55, 50, 45, 40. What if I make a mistake and choose 40 twice? Well, I can always go and click on the cell that I did wrong. And this should be 35. And as long as I haven't stopped recording, if I hit keep, it will repair that one. So do look over your data before you hit stop. Go down to 25, 20, and finally 15. All right, I'll hit stop, and we can see this is clearly not a linear relationship between pressure and volume for my gas. How do we build a model out of this? Well, curve fits are a great way to do that. Curve fits are on by default, but you notice a very large list of drop-down list here to the right of the tool that let me choose some various curve fits, including user-defined. So it's not just these 15. I can define any fit, and Capstone will attempt to fit it to the data you've collected. I'm going to jump directly here to inverse, no offset, because I know that's going to work pretty well. If I want to have students actually experiment with things, they could compare, for example, inverse square and inverse and see which is better. In this case, the root mean squared error for inverse is much lower. There's less error than inverse square. So it looks like, in this case, an inverse relationship between pressure and volume would fairly well describe this. And I could actually derive this equation here. It doesn't have to be Boyle's law. I've collected data. I've built a model showing the inverse relationship between pressure and volume. I could call it maybe Glenn's law. Let me show you one more variation on this, especially popular in pedagogical approaches like modeling physics. I'm going to add another graph below and basically duplicate what I have above for starters. I have pressure versus volume. If you want to make everything linear, what you can do is use quick calcs. I know that I suspect there's an inverse relationship between pressure and volume. I'm going to click on volume, the x-axis measurement, and there's something at the top here called quick calc. I could transform this data visually in the graph. For example, I know it's inverse, so let me take the inverse of volume and scale the graph, and now I can see that indeed linearizes it and lets me use, for example, just a linear fit and look at the R value to figure out that worked pretty well. All right, so we are just a few minutes from the end here. Let me show you one final thing. If I wanted to, I could save this file, and I will, and share it with you afterwards. I'm going to save this as gas, pressure, and volume with data. But what if I wanted my students to not have to go through these setup procedures? Maybe time is short or they're new to Capstone. Well, let me go ahead and change some things. I'm going to turn off the fits because I want them to discover that on their own. So in both graphs, I'll turn off the fits that I found. I'm going to go down here to delete last run and select on it. Or if I wanted to, I could actually use the drop down and delete all runs if I had done more than one. Let me delete all runs. And this file already has the keep mode sampling set up. So I could go in and say file, save experiment as, and call this something like gas pressure and volume config file or template or something along those lines. And I could distribute this file to my students to let them focus on data collection and analysis instead of the setup. All right, Matthew, any questions we should address? Okay, all right. So let me show you some resources, and then we're going to hang out here to address some additional questions I see coming in. So let me jump back here. We are going to have an additional training on Capstone, another free online training in May. It's going to cover some very neat, more advanced features of Capstone, including displays like scope and FFT for analysis of faster sample rated things like fast circuits or sound analysis. We're going to look at how we can actually generate those sounds with the signal generator. We'll take a look at how we can do calculations beyond just in the table and quick calcs, and we're going to do some video capture and analysis, a very powerful feature that doesn't actually require any sensors. Here is our coming slate. I'd highly recommend signing up for the Advanced PASCO Capstone session that's going to cover those things. We tend to fill up pretty quickly. It's going to be on May 8th, and you can register now at pasco.com/online training. We have some other trainings coming up, but if there's a training that you don't see here that you want, we do custom trainings online and in person. You can contact us at training@pasco.com. I'm going to leave you with this resources slide. The most important thing here is the URL in the box down here, and I'm going to type that in the chat window to make sure you get it. I will also email it to you tomorrow with the recording of this session. It is bit.ly/capstone-spring19 for 2019. That's in the chat window now as a hyperlink, and that will allow you to get this additional resources hyperlink document along with some other resources. let me mention just a few things here. We have a very good set of YouTube movies on introducing Capstone. So if you want to go a little bit deeper than we were able to today, take a look at our PASCO Capstone Getting Started playlist there. We have a bunch of little Capstone hidden gem movies, 1-minute movies called How Do I movies that show you how to use little features in Capstone that are answers to frequently asked questions. I've linked some more popular hidden gems here, and our emails here if you have additional questions in the future. So we have just about reached the end of our time together. We will stay here for questions, and I want to show you one final slide here. One of the documents that will be shared at bit.ly/capstone-spring19 is a little challenge. If you want to practice some of the things you've learned today and you don't have PASCO sensors, or you just want to use some canned data, I've collected some data here of a temperature sensor inserted into a beaker of room temperature water that's been stuck in the freezer overnight. And I challenge you to try some of the things you've learned today. I've listed here 14 things to try that you should be able to do now with the skills you've learned about Capstone today. Well, we have just finished here in the nick of time. I want to thank you so much for joining us today. That was kind of a whirlwind tour of Capstone, but hopefully you saw some of the key features that can get you started in the first 20 or 25 minutes, and saw some flourishes at the end that will allow you to do more with Capstone with your students and your own investigations. We thank you so much for joining us today, and understand that most of you need to leave right now. You can simply close Go to Training and close out the session. There is a brief poll at the end. We appreciate your feedback. This is just a 5-question poll. If you have 1 minute to fill that out, we do appreciate your feedback and help us inform future trainings. But we will be sticking here for any questions that you have. So we're going to scroll back up that list. I know some questions came in. And if you have any questions right now, go ahead and send them in the chat window. We'll be addressing them as long as you do have questions. All right, Matthew, what are some of the questions that remain? Okay, so let me the poll is something that's going to pop up as soon as you close Go to Training after you end the session. Great, thanks so much for everyone who needs to leave right now. Let's see. Yes, yeah, Park, I see that you sent some questions to me only, so let me try to address those. A log graph representation is needed when plotting the relationship between resistance and current. At this time, we cannot do real log plots. However, we can use the calculator that we're going to cover in our advanced PASCO Capstone session to transform and take the log of any measurement. So you may not have noticed, for example, log as one of these quick calcs, but the quick calcs are basically, as the name implies, a way to get some more popularly used things. It turns out we can use the full-blown calculator that we'll cover in the next session to take the log of any measurement, or much more than the log if we're interested in that. All right, another question from Park, great. The graph displays the background of the x-axis represent log format. A similar question, yeah. So it is not, but we can transform the measurements and display them in a null-log plot. Thanks, Kurt. So if you have additional questions about things we covered or did not cover, please send them in the chat window. We'll try to address them. All right, so John Long asks, is there a lesson on using the old analog photo gates? I have in mind the PASCO projectile motion experiment by using 2 photo gates, an analog adapter, and velocity time between gates. Yeah, I did not get to show you these things, but let me do that now. Turn off my webcam and switch over to a browser. So among the resources here is a great one. And again, you will get this hyperlinked document. This thing called pasco.com/digital-library. I'm going to open that up in my browser window and show you that. It's pasco.com/digital- is optional, digital library. And this is actually a fairly new thing, and we have put about a decade of labs that we have previously and continue to sell in lab manuals. We put the student versions in the digital library here, so you can download these. And unless you need the teacher answers, and this is publicly available, so we don't put them there, you don't actually need the lab manual itself. So, John, depending on what level you're going for, what I would do is probably search projectile here in the search window, and you can say that's physics, and you can filter out the grade levels here. Maybe it's high school, advanced placement, university. It's going to show you a filter through all of our library files, hundreds of them, and show you some that have the word projectile in them. Now it turns out I can just click on, for example, this first one here, which is kind of a AP, Advanced Secondary School Lab, two-dimensional motion projectiles. I'll click on it and I can see that this uses the SmartGate PhotoGate. It would be translatable into the traditional PhotoGate, and if you wanted to use it, you can download the Word file and Capstone config file. But let me go back to the search results here and see. I know there are some earlier labs represented here, so here's one that uses the more traditional digital PhotoGates. All right, yep, this one uses PhotoGate. So here's an approach that might be a little more advanced secondary level, but one way to get to it. So go ahead, John, and do a search in the digital library. I think you'll find what you're looking for there. All right, thanks, Matthew, for the additional info there. All right. Yeah, Park. So you can use the calculator to take the log of a measurement and then display that on a graph. It's technically not a log graph because it is showing linear jumps, but the values are logified. And the way you'd use that in the calculator is to come in here, and we'll cover this in the next session, but you can say something like log of p. In this case, I'm going to say log p. This is kind of like an assignment in programming. The output of my calculation is going to be log p, and I can come down here to the use here, scientific, there it is, log. It's going to say log of whatever I want. And the trick here, again, is to right click. If I right click in log here, I can say it's the log of pressure. I'll put it in there, I can define the units. But as soon as I've done that, basically any graph that was previously showing a direct sensor measurement can be switched to show the log value of that measurement. Thanks for your question. All right, Vasek, thanks for your comment, Vasek. All right, we're going to stay here. If there are additional questions, don't hesitate to send those to everybody and we'll address them. I'm going to go ahead and stop the recording at this time and you'll receive a copy of it tomorrow.